Okay, so good morning to all of you. I expect to have a lot of people today because we have both MSc students and and BTech students. So I'm covering the harmonic oscillator in quantum mechanics, um, and the harmonic oscillator is one of the most important topics. In fact, as some um, famous physicists have made this observation before that much of theoretical physics is simply the harmonic oscillator at higher levels of abstractions. So, you begin with talking about, for instance, the electromagnetic field. The electromagnetic field, when you quantize it, you describe it with harmonic oscillators. When you talk about quantum field theory, the scalar field, that is also becomes a collection of harmonic oscillators. When you talk about something like string theory, string theory turns out that this oscillating string is described by a bunch of modes, which are also a collection of harmonic oscillators. And so the underlying reason for behind all of this is because of the fact that we are using a tool which is common to all of these, which is Fourier analysis or spectral analysis, right? So that is the fundamental tool that is being used wherever we have differential equations, and all of these fields, whether we are talking about the electromagnetic field or scalar field, or whether we're talking about a string, we are always solving some equations of motion or free particle. And all of these equations of motion, they involve they involve differential equations. And the way we solve linear differential equations, and the way we solve these linear differential equations is using the Fourier analysis, right? So when you do Fourier analysis, what happens is that you write down the solution as an expansion in terms of Fourier modes, you insert that into your equation, and then when you take derivatives, what happens is that spatial derivatives become converted to powers of the momentum squared, and time derivatives are converted to powers of the angular frequency omega squared. And so you are left with instead of a differential equation, you are left with a polynomial equation. When you find the roots of the polynomial equation, you substitute that back into your Fourier expansion, and that gives you the general solution. So when you quote unquote quantize the theory, what is actually being done is that we are taking these Fourier modes, and we are associating each Fourier mode with a single harmonic oscillator. And that is what each Fourier mode actually is, right? In Fourier analysis. So a single Fourier mode is just a plane wave, right, of the form exponent I plus minus I kx, right? And what is this? This is a plane wave, and a plane wave is a solution of the equation of the simple harmonic oscillator. So, so as I said, most problems in physics boil down to solutions, to writing down, to decomposing the solution in terms of harmonic oscillators. So, okay. Now, before I start talking about the harmonic oscillator, let me give you all the homework number 4, the problem for homework number 4. I think I've given some problems in class before, but this is the main problem. And this is for both BTech and MSc students. So this is the problem. You have a particle on a line where potential is defined in this way. So instead of a potential well, what you have is a potential barrier. And you can say this is x is equal to 0 and L. And the width of this barrier is L. And you have 3 regions, as in the case of the potential well. And what you do is you again write down the Schrodinger equation for the wave function in all 3 regions separately, right? So the question is basically write down Schrodinger equation for 3 regions. Then apply boundary conditions. So where at the boundary conditions would be, where are the boundaries? X is equal to 0 and x is equal to L. And apply boundary conditions to determine relationship between the coefficients, right? So you can write down and also solve. So you can write down the general solution. Once you have the Schrodinger equation, you can write down the general solution between the coefficients of the three solutions. Okay. And then use this to find the ratio of this amplitude psi, the wave function psi of x defined in region 2. So this is region 2. So the wave function defined in this region at x is equal to L, the amplitude of this squared divided by the amplitude of the wave function in region 3 defined at x is equal to L. Sorry, not x, at x is equal to 0. Or either way, you can, maybe it's better to say this. And what this tells you, what this gives you, is the probability of the particle that the particle will tunnel through the barrier. And this is for when the energy of the particle is less than V naught. Okay, so this is the homework problem. And as discussed with the BTech students, this homework problem along with the others is due by Friday, but for those who are occupied in some way can turn it in by Sunday. Okay. And then the goal is basically that I can give you the last week before your final exams off. So you don't have to, come to class anymore. Okay, all right, great. So are there any questions before we begin from previous classes? Okay, all right. So today we are going to talk about the harmonic oscillator. Before I talk about the harmonic oscillator, I just wanted to mention again some good news for my MSc students, because for the BTech students the class is almost over. But the pen for my tablet has I have been tracking the delivery, and it has left. The flight has departed from Beijing city on 2nd November. So that means that by the grace of the gods of Indian customs, it should arrive here sooner rather than later. And then you will not have to deal with viewing things on the small screen, and it'll maybe things will become a little bit more convenient. So before talking about harmonic oscillator, I want to talk a little bit about Hamiltonian mechanics. Okay. So what you know is that, well, we can write down a Hamiltonian which has this form, where T is the kinetic energy, U is the potential energy, and so what that means is that H, this object H, is basically the total energy, right? Now, what you find is that when we write down Schrodinger's equation, is that Schrodinger's equation takes this form. Okay, and for the MSc students, I have not introduced Schrodinger's equation in this form, but I will come back to this when we have our own MSc only classes. Okay, and perhaps you have seen it in your BSc courses. This is just Schrodinger's equation. You have the Hamiltonian operator acting on the left, and on the right you have this time derivative. Right. So this is what is the general Schrodinger's equation. And yeah, my writing is very bad. I apologize for that. Part of it has to do with having a small screen. So what is this? What is this H bar? This H bar is basically, you take this Hamiltonian of classical mechanics, right? And you quantize it. So what do we mean by quantize? Well, we have, for example, the kinetic energy T, and that's written as P square by 2m, right? For a particle, for a free particle, for a single particle. And what would it mean if you were to quantize it? Well, to quantize it means that you take the quantity, the number P, and replace it by the operator for the momentum. And the operator for the momentum is this expression, right? This is in one dimension, by the way. If you are in more than one dimension, in general, it's minus IH bar, the gradient, right? In general, it's a vector operator. And what about the potential energy? The potential energy U, well, it can depend on it depends on the form of the potential energy can have different forms, right? So for example, so it's generally some function of position, but it can also be a function of time. You can have a time dependent potential energy. And so how do you quantize it? Well, you take your position operator and convert it into an operator, right? Now, what happens is that when we look at this wave function, we don't usually deal directly with the full state psi, right? The state psi can be written as some in terms of some set of basis vectors. So what we actually deal with normally is these operators H and whatever acting on these basis vectors rather than on the full state. So and so this is the representation. There is some particular choice of representation that we make, and that is the choice of the basis. So one particular choice is called the momentum representation, right? So in the momentum representation, sorry, position representation. This is the position representation. We take our basis states, these basis states, to be the position eigenstates. Basically, the position operator acting on these states just gives you the position of the particle, the location x. And psi of x becomes, so psi of x, which is often incorrectly identified as the wave function. Psi of x is not the wave function, right? It's just a component, the x component of the wave function. The full wave function, the full state vector is this ket psi, right? So what we generally deal with is this state psi of x, are these components psi of x. And so when we take this potential energy operator and act on this psi of x, what happens is that, well, x, since the action of this operator is trivial, your potential energy function also just becomes a function of x rather than an operator. So as an example, if you think of u is equal to 1/2 kx squared. Now what is this? This is the potential energy for a simple harmonic oscillator, right? And if you write down the operator, what do you get? Well, the operator is 1/2 kx hat squared. Now when I introduce this into the Schrodinger equation, I will have this term, right? When I write down h acting on psi in the Schrodinger equation. So what is h? H is t plus u, right? So the t part, the kinetic energy part, will be given by this expression squared by 2m. And the potential energy part is this operator acting on the state psi of x. So this can be written as u of hat using the expansion of the state psi in the position representation, right? I insert this expansion over here and I get this operator u acting on psi of x, x dx, right? So this is an operator and psi of x is just a number, right? So this operator will act on this state x. So I can write this as u acting on psi is equal to integral psi of x, operator u acting on the state x dx. Okay. And what is the operator U? The operator U is U hat is 1/2 kx hat squared. So if I take this 1/2 kx hat squared and act on the state x, what do I get? Well, I just get 1/2 k x squared times x, right? Using this property of the position eigenstate. So I just have x hat squared is just the operator x acting twice. That will just give me 1/2 kx squared. So what will happen is my Schrodinger equation, my final Schrodinger equation will take this form. D square by dx squared psi of x. So, okay, this is, sorry, too close to the edge of the screen. So maybe I'll just start on this page. So my final Hamiltonian operator will become T plus U. What is T? This is my T, right? Or T hat. And what is U? U is 1/2 k x hat squared, right? So when I write down h hat acting on psi, remember that h hat acting on psi is actually this expression. Psi of x, h hat acting on the position eigenstate dx. Okay. So sorry, should be careful with this. H hat acting on psi of x, x dx. I can't take h hat and psi of x to commute because h contains derivatives of the position, and so the derivatives, that derivative operator will act on psi of x. And so the full expression here will become minus h square by 2m square d square by dx square psi of x. This is the kinetic energy term plus 1/2 kx squared. Why? Because when this operator for the potential energy acts on this expression, what will happen? I will just get the function of x, 1/2 kx squared times x dx, right? And then on the right hand side of the Schrodinger equation, I have I h bar d by dt of psi, right? And in general, psi will be a function of x, of position and time, right? But if we take psi to be an eigenstate of the energy operator, right? Then this can be just be written as E psi. Right? What is the energy operator? It's just this guy. So if I again substitute this expansion of psi in this expression, the right hand side will become E times psi of x get x dx. Okay. Let me see if there are any questions on the YouTube channel. So so now what we do is so this is the left hand side. This is the left hand side of the Schrodinger equation, and this is the right hand side. And we equate these two, right? So this is the LHS and this is the RHS, right? And we equate these two. So when we equate these two, what happens? We have this expression is equal to this expression, right? And what is this expression? This is a vector, right? This whole thing is a vector. These are the basis states of that vector, and this guy in the brackets, these are the coefficients of that basis, right? These are the basis states and these are the coefficients of that basis, of that vector in that basis. So when you have two vectors, when you have this guy and this guy, when you have two vectors, they are equal to each other, right? And you're working in the same basis, right? So when you have u is equal to v and u is equal to, let's say, summation of some coefficients u of I ei, and v is equal to v of I ei, okay? Then this is only possible if u of I is equal to v of I for all I, right? Each component has to be equal to the corresponding component, right? So this means that I can set this quantity in brackets equal to this quantity here, right? So I can write this expression minus and this is what is normally referred to, quote unquote, as Schrodinger's equation, right? For the, in this particular case, for the harmonic oscillator potential. But again, you have to keep in mind that the actual equation is this expression, this guy, right? And what is this expression? This is the Schrodinger equation in the position representation, right? So one could equally well, instead of using the position representation, we can also use the momentum representation. We can write down the eigenstates of the momentum operator and expand our state in those eigenstates. Then we will get a different expression for this equation. What will happen in that case? When you go to the momentum representation, this, instead of derivatives with respect to, so what happens is, right, when you're in the position representation, so in the position representation, this is what happens to your, again, I'm sorry, writing is coming out to be so bad. This is what happens to your momentum and position operators. And in the momentum representation, what happens? In the momentum representation, your P operator just becomes the number P. And your X operator, any guesses what happens to your X operator?
It becomes the derivative.
It becomes
it becomes the derivative, d by dp.
Right, d by dp. Is there any factor of h bar?
I don't know, sir.
There has to be a factor of h bar because otherwise our units will not match. Okay. So where should that factor of h bar be? That factor of h bar will be here only. Right? You can look at this first expression. You can see that p hat divided by h bar gives me d by dx. So 1 by x. So x goes as h bar by p. So h bar has to appear here. So when we talk about solving the Schrodinger equation, we have to solve this expression. Okay. Any questions so far? Oh, Yukta found the YouTube link because she's actually watching it on YouTube. So I think we are fine. Yeah, my Telegram got stuck, so I couldn't share on the book. Okay. Is this okay so far? Maybe I'm moving a little bit fast. If I'm moving too fast, you please stop and tell me, okay? All right, so now we can talk about the solutions of this equation. Now we can ask, well, how do we solve this equation? Okay, so this is our Schrodinger equation for a particle in the potential of a harmonic oscillator. Okay, and what does the potential of a harmonic oscillator look like? So this is x, right? It just looks like a polynomial function, right? It just looks like a parabola, x squared. Okay. Now what will happen is our energy levels, when we solve Schrodinger's equation, we will find that the energies E can only take on a set of discrete values. So these are the energy levels. And there is a discrete set of energy levels and there is an infinite number of them. Okay. So now we have to solve this expression. Solve this equation. Okay. Now there are two ways to solve it. There are probably many more ways to solve it, but two ways that I know of. So one way is to just look at this. One way is to just look at this as a differential equation. This is an ordinary differential equation, right? So it's an ordinary differential equation, which looks like this. Right? Now, this kind of an equation, you can, when you what you can do is there are different ways of solving such differential equations. One of them is to write down a series expansion of psi of x. You write down psi of x. You write down a psi of x as something as some polynomial function of x. So what is it? Something like this. Let's say Rn x to the n, something like this. X goes from 0 to infinity. Then you substitute this expansion into this equation. You get certain recursion relations for the coefficients.
Sir, wouldn't it be n from 0 to infinity?
Thank you, Ashantanu. And sorry, Shantanu, not Ashantanu. So it is n, yeah. And then we solve this. And you can also have n from minus infinity to infinity. It depends on the, I mean, in general, this will be from minus infinity to infinity. One has to be careful about, the points where the function will blow up. So that will set certain restrictions on your coefficients. And then what you'll end up with is that your functions turn out to be, your solutions turn out to be something called Hermite polynomials. And these are some polynomials in X. And so the h of 1x is just 1, h of 2x, I think it's x. And then the higher order polynomials have powers of x, and then there's some functions of cosine x and so on. And then your state turns out to be something like this: e to the minus some alpha x squared times the Hermite polynomial, something like this. This is in general, the solution of this differential equation. Okay, but this is the hard way to solve this problem. So this is the hard way. Okay, then we have an easier way. And this is due to Dirac. Right? You remember this whole bracket notation, it comes from Dirac only, right? So what is this? This is the method that is also explained in Barak Shoshani's lectures, okay? Now, let's see. So what is this general solution? How do we do it? Well, let us look at this expression, and we will see that we can do something with this expression. So let me write this as minus h bar squared by 2m d squared by dx squared, or, well, what is it? This is p hat squared by 2m plus 1/2 kx squared acting on psi of x. Okay. Now, this expression has the general form of a square plus b square. Okay. Now, when I have, whether you talk about operators or numbers, it doesn't matter. When I have a square plus b square, I can factorize this expression in this way, right? I can write down a square plus b square as the product of a plus ib multiplied by a minus ib, right? So when I take this, what will happen is, well, at least in the case, so again we have to be careful. At least in the case when we are not dealing with operators, the BA term will cancel the AB term. Okay. So that's why I removed the hats. Now, when we are dealing with operators, then the commutator will play a role. So if I write down this expression, so this is just for numbers, okay? But if we have operators, what will happen? If we have operators, then if you look at the right hand side of this expression, I will get a square and b square, right? But I will also get, if I, so just expand out this expression on the, what will I get? I'll get a square plus b square, but then I will get I times BA minus AB, right? So that means that if these guys are operators, then a square plus b square can be written as a plus ib, a minus ib, minus I, or I'll take plus I times a hat b hat minus b hat a hat. Okay, so I've taken this term over to the other side and then I've switched signs. So instead of BA, it becomes minus AB, it becomes AB minus BA. And what is this? This is the commutator of A and B, right? Okay. So now if you look at these two expressions again, this is A square. What is A square? Momentum squared. B square is position squared. Okay. So then what I can do is I can write the sum of these two terms. This is P square and this is X squared, right? So I will write it like this schematically, capital P plus capital X squared. Okay. So capital P is this whole thing and capital X is this whole thing, becomes equal to P plus IX, P minus IX plus the commutator of capital P in X. Okay. Now what is capital P? It's minus minus IH bar d by dx small x. And what is capital X? 1/2 sorry, root k by 2 times x. So what is the commutator of these two, capital P and capital X? So capital P is minus IH bar, and then there is a root 2m, right? I'm talking about the square root of this whole thing. So the square root of that will have a root 2m in the denominator. So what will this be? This will just be, I'll get root k by 4m times the commutator of the momentum and the position x and p. Okay. This commutator we know very well, right? It's just the commutator of the derivative and the position. And this commutator is equal to minus IH bar, right? So this just becomes minus IH bar by half root k by m. This is the commutator. Okay. So this commutator is just a constant, right? That's the most important part. This commutator turns out to be just a constant. There is no dependence on the position. And that is why this factorization works. Okay. If this was some function of the position, for example, then we would not be able to use this method in a direct way. Okay. Okay. So great. Now we can factorize it. So what? So so now we need to look at what these operators are. Okay. So I have P plus IX. Okay. I'm going to call this A hat, and I have P minus IX. Now, if you remember, momentum is a Hermitian operator with the caveats that it applies only to L square integrable functions. It's Hermitian only on square integrable functions. And position is also a Hermitian operator. So when I take P plus IX and I take the Hermitian conjugate of the whole thing, what will I get? I'll get the sum of the Hermitian conjugates of the two separate terms. And since P is Hermitian, so P dagger will just become P, X dagger will just become X. But when I take Hermitian conjugate, I have to take all the complex values also have to be conjugated. So I becomes minus I. Okay. Right. I will give lots of numerical problems. Don't worry about that. Okay. So the numerical problems will come, but we're doing theoretical physics. So it's the theory comes first, right? And so this guy can be written as this operator A Hermitian conjugate. It's A dagger. Okay, so we have these two operators, A and A dagger. these operators, they are known as, there are different names for these operators. They are known as ladder operators, also known as annihilation or destruction, and creation operators. So sometimes people call it annihilation, sometimes people call it destruction. They both mean the same thing. So they are also known as annihilation and creation operators. So this operator A is identified with annihilation, and this is identified with creation. So what does it mean, annihilation and creation? We'll see in tomorrow's class. Okay, so they both one creates something and the other annihilates something. And what actually happens is that you start with some, if you start with some vacuum state, then the action of A on the vacuum state just gives you 0. The action of the creation operator on the vacuum state gives you the first excited state. So I'm writing that as ket1. So if you act on the nth excited state, you get something which is, you get the n+1th excited state with A dagger. And similarly, if you act with A, what happens is your energy level goes down by 1 step. So that's why these are called ladder operators. So this is the energy, and if you want to climb up the ladder of energy, you apply A dagger repeatedly. If you want to go down the ladder of energy, if you want to go up, you apply A dagger. If you want to go down, you apply A. And each time you apply the operator, you go up or down by 1 step. So we will see tomorrow, in tomorrow's class, how this happens. Okay. So, but I'll stop here. I think this is enough material for one class. So what are the things we have talked about? We talked about this Hamiltonian operator, and also this homework problem. Okay, this is homework problem number 4 for the 4th homework set, and plus whatever other problems I've given you in the previous classes. Okay. All right. So questions. Any questions? No questions? Okay, so Akash is asking, when you say momentum representation, what exactly do you mean by that? Well, what I mean is eigenstates of the momentum operator. Akash, you are MSc student, right? So I will talk about this momentum representation with you guys separately. Okay, we have not covered it in your MSc yet. We will come to that. Momentum representation just means eigenstates of the momentum operator, and the momentum operator is basically this derivative. Momentum operator is just this derivative, right? So the eigenstates of this derivative operator are just the plane waves, sine and cosine, or linear combinations of sine and cosine, or exponent e to the I plus minus kx. Okay, so all right, thanks for coming. Class is up. Of course, I'll stay for another few minutes for any questions. Yeah.
So for the harmonic oscillator part, are we referring to the only the kinetic energy equation, or are we referring to the equation as a whole?
We are looking at the whole equation, no? Because we are looking at the whole equation, p squared plus 1/2 kx squared. You're talking about when we do this factorization, right?
So then how is it harmonic?
What do you mean? How is it harmonic?
Like when we are referring to harmonic oscillator, we need a harmonic equation, right? And for this only 1/2 kx square is harmonic.
No, this is the harmonic oscillator. This is what gives you the equation of motion of this. It turns out is the equation of motion for a spring. This is the harmonic oscillator equation. If you want, I can show that. So shall I show it? Shantanu?
Yes, sir.
Who was asking that question? Utsav or Shantanu?
Sir, Utsav.
Utsav, right? So the harmonic oscillator equation comes about like this. So basically what you have is, again, this is a part that I have not covered with the BTech people. I skipped it, which is that once you have the Hamiltonian, you can write down the equations of motion of the system. So what are the equations of motion? So the Hamiltonian is some function of position and momentum, right? But the equations of motion should tell us what are the time derivatives of the position and momentum, right? That is what we mean by equations of motion, right? So it turns out that we have something called Hamilton's equations, and these Hamilton's equations are equivalent to basically writing down Newton's second law. But to get to the formulation, you have to go through this different route involving Lagrangians and least action. I didn't want to do all that for the BTech people. So Hamilton's equations tell us that x dot, so x dot means dx by dt is equal to dh by dp, and p dot is equal to minus dh by dx. Okay, these are the equations of motion for a system which is described by a Hamiltonian. Now, if your Hamiltonian is this expression, p squared by 2m plus 1/2 kx squared, then what is dh by dp? Dh by dp, this term does not depend on p, so this will just be 0. This term will give you p by m. Okay, and what is dh by dx? This term does not depend on x, it will give you 0, and the other term will just give you kx. Okay, so substituting these expressions in Hamilton's equations, what do I find? I find that x dot is equal to p by m, and p dot is equal to minus kx. Okay, now I take a second time derivative of both of this equation. So I take a second time derivative of this equation. What does this give me? On the right, it gives me x double dot. On the left, it gives me x double dot. On the right, it gives me p dot by m. Then I can substitute this expression for p dot over here, and that gives me minus kx by m. So finally, I'm left with one differential equation, which is x double dot. What is x double dot? Dx squared by dt squared is equal to minus kx by m. What is this? This is just the equation for simple harmonic oscillator, right? Yes.
Yes, sir.
Okay. So this expression describes the mass which is connected to a spring, or any system which can be described in terms of Hooke's law, basically. So this is the harmonic. This is where you get the harmonic oscillator from. So if you write down solutions of this equation, what do you get? You get x of t is equal to a cosine omega t plus b sine omega t, where omega is equal to root k by m. Okay. I suppose I'll talk about this again in tomorrow's class for the benefit of everybody else. Okay. Any other questions? Okay, I'll stop the recording.